In previous lecture, we know that paramagnetism is coming from the Hamiltonian. I'm sorry. Paramagnetism. The paramagnetic Hamiltonian is like has a term mu b and L plus GS dot B. This is paramagnetic term. Anyway, the paramagnetism is the positive magnetic susceptibility, but there is no spontaneous magnetic ordering. And paramagnetism is the positive magnetic susceptibility, but there is no spontaneous magnetic ordering. As you know, this paramagnetic term has the orbital angular momentum and spin angular momentum. Therefore, in order to have the paramagnetic signal and partial field orbitals, there should have the partially field orbitals. And if there is unoccupied electrons, the atoms have non-zero magnetic moments. For example, as we said, angular momentum has the 2, 1, 0, minus 1, 2 for L equal 2 case. If there is, for example, spin like this, then 3 electrons occupied in each orbitals, and the total orbital angular momentum is 3, and the spin angular momentum is the 3½ times. Therefore, and total angular momentum L plus S is like that, and it is a non-zero value, and there is a finite angular momentum. Therefore, in previous talk, I say that fully occupied orbitals do not have a paramagnetic term. Here, for zero magnetic field, without applying magnetic field, spin points in the random direction. Points in spins, point, random directions. But by applying magnetic field, and magnetic field aligns up with the applying magnetic field, spins line up along the field direction. Depending upon the strengths of field. Then here the total angular momentum is like that. Anyway, plus minus S. It is total angular momentum. I will discuss later then how to calculate the total angular momentum, what is plus and what is minus. It is coming from the Hund rule. To understand this paramagnetism, let's treat it as a semi-classical method. Here, let's consider for magnetic moments lying at an angle by applying magnetic field. This is magnetic field direction, and the spin lining up but we already know that spin precesses by applying magnetic field, and by the spin precession, here let's consider is there is an angle theta with applying magnetic field. This is magnetic moment direction. Then we can consider here there is a sphere. There is a sphere like this, and spin precesses as an angle between the magnetic moment direction and the magnetic field direction, and here spin precesses, and here small deviation of d theta. Here is d theta deviation can be applied. Here in this case, the energy is that minus mb cosine theta. Here let's denote as b, because it is m dot b. The fraction of magnetic moments, here the fraction of magnetic moment lying at an angle between theta and theta plus d theta is that here, because it is if we say that it is unit angle, unit magnitude, then it is sine theta. Therefore, it is 2 pi. Sine theta is the circumference of this circle, and d theta is the deviation of the angle. Total surface on this blue sphere is 4 pi. Therefore, the fraction of magnetic moment at any angle is that 1 over 4 pi times 2 pi sine theta d theta. Therefore, it is 1/2 sine theta d theta. Therefore, we can calculate the average magnetic moment along B field. The average magnetic field along B field can be calculated as a fraction the G direction. Here is the G direction. It is a G direction, and the average magnetic moment is coming from the total. Here the Boltzmann, we know that it is a Boltzmann factor should be considered, and the angle between Boltzmann factor exponential minus beta energy, beta epsilon, is a Boltzmann factor, and the fraction of the magnetic moment at any angle is that 1/2 sine theta d theta, and the theta is the range from the 0.pi. And also in the numerator, and from 0 to pi, and mg and exponential minus beta energy, and 1/2 sine theta d theta. You know, beta is the 1 over tau, 1 over kBt. It is a reciprocal temperature. And because the energy is that minus mb cosine theta, is that integral 0.0 from 0 to pi exponential mb cosine theta over kbt and sine theta d theta and integration from 0 to pi m cosine theta. In the g component of magnetic moment is m cosine theta. M cosine theta exponential mb cosine theta over kbt sine theta d theta. Here, in order to calculate this integral, let the cosine theta is x and y is that mb over kbt is y. Then dx is that minus sine theta d theta, and from here this the numerator term, it is a star. Let's think about the numerator and as exponential. When the zero means that in the zero case is 1 and the pi is minus 1, but the minus sign is coming from the d theta, sine theta d theta minus sign, and the range is flipped, therefore from minus 1 to 1, and also exponential xy sine theta d theta is dx. Then it is that 1 over y exponential y minus exponential minus y from the here, therefore the average value of the g component magnetic moment is that m is constant, and also integral minus 1 to 1 exponential xy dx, and the numerator is that minus 1 to 1 x exponential xy dx. And the numerator, it is a 2 star, and the equation of 2 star is that integration minus to 1 x exponential xy dx is the less integration by parts, and also integral of exponential, it is that 1 over y exponential xy, and x equal from minus 1 to 1 minus, and here minus 1 to 1 over y exponential xy dx. Then it is that 1 over y exponential y plus minus and plus exponential minus y, and also minus 1 over y squared exponential y minus exponential minus y. Therefore, this mg is that it is the denominator and is a numerator, and therefore the first term is that exponential y plus exponential minus y over exponential y minus exponential minus y, and the second term is that minus 1 over y. Therefore, and also here m, therefore it is m cotangent y minus 1 over y. Here we define that it is a Langevin function. It is a Langevin function. cotangent y minus 1 over y. It is a Langevin function, and it is that mg over m. It is a Langevin function. From history of science, Langevin, it is known that Langevin is kind of very genius, and Einstein said that Langevin can discover the special theory of relativity when I do not find the special theory of relativity, and like that, Langevin was very genius. But it is, unfortunately, he married with very bad wife, and that's why he did not concentrate on his research, and also he was the student of the Pierre Curie. Pierre Curie is the husband of Marie Curie. And after dying of Pierre Curie, Langevin become the students of Marie Curie. Anyway, and the Langevin function is that defined like this, and for small y, and cotangent, hyperbolic cotangent, hyperbolic cotangent. Hyperbolic cotangent y is that cosine hyperbolic y over sine hyperbolic y. And also it is that exponential y plus exponential minus y, exponential y minus exponential minus y. When we multiply exponential y into size, and the exponential 2y plus 1 and exponential 2y minus 1, and also from the some mathematical manipulation, and it can be expanded like that, 1 over y plus y over 3 minus y cubed over 45, and so on. Therefore, the cotangent, the Langevin function is kind of cotangent y, hyperbolic cotangent y minus 1 over y. Therefore, it is y over 3 plus order of y cubed in the higher term. Therefore, the saturation, if the saturation magnetization can be defined at Nm. Here, N is the number of atomic moments, N is the number of magnetic moments. For unit volume, and the magnetization is that n times average value of magnetization. Therefore, the magnetization divided by the saturation magnetization is that the mg over m. Therefore, mg, expectation value of the mg is the m Langevin function. Therefore, then mg over m is that Langevin function is order y over 3 for small y. Small y means that it is the my can be defined mb over kBt. Small y means that the low magnetic field and high temperature. Also, low magnetic field and high temperature. High temperature enough for room temperature, and magnetic field also can be considered very small in conventional magnetic field. The magnetic susceptibility is m over h, or the mu 0 m over b. Therefore, it is that n mu 0 m square 3 kBt. Then it means that magnetic susceptibility is proportional to the 1 over T, and we know it is known as the Curie law. Here Curie is the Pierre Curie, the husband of Marie Curie. It is Curie's law, and magnetic susceptibility is inversely proportional to the inverse proportional to, here C is Curie constant and temperature, and it is known as Curie law. Therefore, in the paramagnetic case, chi over T shows that 1 over T dependence, and 1 over T dependence, and in other words, when you draw like in the chi 1 over chi versus T, there should have the linear dependence. It is a Curie law. It is a semi-classical treatment because we consider for the integral. Integral is continuous magnetic moment, and the magnetic spin can have the arbitrary direction, and it is a semi-classical treatment. Semi means that this expectation value formalism is similar to the classical statistics. And also, let's consider for the quantum mechanical treatment. And the quantum mechanics means that the spin do not have the arbitrary direction. They should have the quantized direction. And here it is a quantum mechanical case, quantum mechanical treatment. Here the parameterism for J equal to 1/2 spin lining up, spin up or spin down, because for quantum spin and J equal to 1/2. In other words, the MJ is indicated plus minus 1/2. Here, if there is a degenerated state, by applying magnetic field, there is the spin degeneracy. One is that the 1/2 spin up, and minus 1/2 it is a spin down, and here magnetic moment is mu b, and also minus mu b. Therefore, the energy splitting is that G mu b is spelled B. It is known as a Zeeman splitting. Therefore, the expectation value for the G mu b G mu b mg is the expectation of the magnetic moment from the quantum statistical mechanics partition function, and here G mu b is a constant, and also mj is a discrete value, and mj exponential minus beta energy ej. where the g is the partition function and the summation for each j exponential minus beta ej. It is a partition function. As you know, partition function is very important in statistical mechanics, and if we know that partition function, we know the system everything. Therefore, here there is two possibilities. One is a spin up and spin down. It is very simple to calculate, and also g mu b mg case is that one partition function, one spin up. Spin up is that energy mu b exponential beta ubb, and also plus the other one is the minus beta ubb. It is a partition function, and also the numerator, yes, mg is 1/2 and the g equal to 2 cancel with each other. Therefore, it is a minus mu b exponential beta mu bb is that the spin down case, and for spin up case, and here plus mu b exponential minus beta mu bb is that. Therefore, it is that when you subtract the mu b in here, it is a hyperbolic tangent. It is that mu b hyperbolic tangent over mu bb over kbt, because beta is kbt. It is hyperbolic tangent. Here, let y equal ubb over kbt. We already defined previously. It is that basically, when you write down as full moment, it is gj ubb kbt. We here this y term is coming from the j equal 1/2, and lambda g factor is 2. Therefore, it is that m over saturation magnetization is that mj over j, and it is that hyperbolic tangent y. Therefore, for small y, small magnetic field and high temperature, and the hyperbolic tangent y is close to y, and also it is mu bb over kbt. Therefore, from this magnetization, magnetic susceptibility is that u0m over b is that and mu0 mu b square and kbt. Also, it is followed that 1 over t dependence. It is also consistent with semi-classical treatment. It is also Curie law. Anyway, we know that in other calculation, and we already know that partition function on this system partition function for spin down exponential beta mu be b, and for spin up, and it's a spin exponential minus beta mu be b. Therefore, it is 2 cosine hyperbolic mu be b over kbt. From the Helmholtz free energy, Helmholtz free energy can be calculated like the minus kbt ln g. Therefore, minus for in real system, and here n kbt ln 2 cosine hyperbolic mu be b over kbt. The magnetization is that negative partial F partial B for temperature constant. From this definition say that magnetization is that when we increase the magnetic field, decrease the rate of decrease of free energy. It is a definition of magnetization. Therefore, it is n kbt over 2 cosine hyperbolic mu be b over kbt, and also in the 2 kb mu b over kbt and sine hyperbolic mu be b over kbt. Therefore, it is kind of 2 to cancel with each other, and n mu b tangent hyperbolic mu be b over kbt. Therefore, m over ms is that hyperbolic tangent mu be b over kbt. Here it is the simple description for the spin up state or the spin down state, single electron. And we should think about that. We should think about for general spin state. And also, how about general spin state? In previous case, we only consider for the spin up and spin down, and in general case, the spin has the greater than the 1/2 and less than infinity, and the J value can have the arbitrary value, but it is still quantized in quantum mechanical treatment, and it is a general calculation. And in this case, the partition function is that for mj can choose from -j to j, and also Boltzmann factor exponential beta mj gj mu bb. It is Boltzmann factor. And here, let's denote that x equal beta gj mu bb. Here, because mj is a summation index, other elements of beta gj mu bb denote by x. Then the expectation value for mg is that summation for mj is that from minus j to j is exponential xmj, and the summation mj from minus j to j, and also mj exponential x mj. It is like that the partial x ln g. Yeah, okay. Therefore, in the magnetization is the n gj ub mj, and it is that the n gj ub, and also partial x can be write down as a partial b and partial b partial x. It is that partial x and ln g. Here partial b partial x can be calculated from this relation, and therefore it is ngj mu b partial b partial x is that 1 over beta gj mu b, and also partial ln g over partial b. Therefore it is that nkbt partial ln g over partial b. Therefore, in order to calculate this one, and we should know that the partition function exactly, and the partition function is that mj from minus j to j, and exponential mjx is the partition function, and from exponential minus jx plus exponential minus j plus 1x plus exponential minus j plus 2, like that, and so on to the exponential jx. It is a total partition function. When we extract the summation for I equal to 1 to m, when we extract the exponential minus jx, then exponential I minus 1x. Here, and it is that from this series, from the series calculation, it is 1 minus exponential x, and also exponential minus jx, and 1 minus exponential mx. Okay, and here m is that 2j plus 1, because it is a degeneracy. It is a number of degeneracy, and here let's calculate. It is that 1 minus exponential x, exponential minus jx, and 1 minus exponential x, and 2j plus 1. When you multiply exponential minus x half, then here the first term exponential minus j plus 1 half x minus exponential j plus 1 half x. And also exponential minus x sub 2 minus exponential x sub 2. Therefore, it is hyperbolic sine x sub 2 and also hyperbolic sine here 2j plus 1 and x sub 2. Here, because we know that the partition function in the from this relation, the m is that n kbt is that partial here it is that 1 of g and partial g partial b then partial b partial x from here then the partial b partial x can be considered as a let's copy here and here partial b is that partial x partial b partial x partial b and partial x partial b is that beta gj mu b partial x. Therefore, beta and kbt cancel with each other, and therefore it is n gj mu b and 1 over g partial x. Therefore, here let it is n gj mu bj is the saturation magnetization, and here this the g can be is calculated like this formula, and also then this can make a ngj mu b j, and we define it as a Brillouin function. Brillouin function as a function of here as a function of like this, and gj mu b bj over kbt. Here the x is defined at gj mu b over kbt. It is x as a function of x. Therefore, here the Brillouin function, it is we call it is a Brillouin function, and the Brillouin function can be write down. I do not calculate it explicitly, and it is a 2j plus 1 over 2j and cotangent hyperbolic 2j plus 1 over 2jy and minus 1 over 2j cotangent hyperbolic y over 2j. It is defined by the Brillouin function. You do not remember the explicit expression of a Brillouin function, but you should understand that magnetization has a function of Brillouin function. Here in this case, and when you draw the Brillouin function as a function of y, is a Brillouin function. The maximum is 1. Thus it is 0, and it is -1. It is 0 case. The Brillouin function you can find in the textbook, and also like this for j equal to 1, j equal to 1/2 case, and for infinity j equal to infinity, like this. Therefore, when we measure the magnetization in the paramagnetic materials, the magnetic field dependence of magnetization shows the Brillouin function like. And let's calculate several extremes. And for j equal to infinity, the Brillouin function for j equal to infinity to y, it is that cotangent hyperbolic y minus 1 over y, which is identical with the Langevin function. It is a semi-classical result. And j infinity means that very large spin and spin can be considered as a continuous distribution. And the second case is only for the j equal to 1/2. It is a classical quantum spin. And b 1/2 y is that 2j plus 1 is the 2. Therefore 2 cotangent hyperbolic 2y minus cotangent hyperbolic y. Then it is that yeah, you know. And let's write briefly for the hyperbolic function formalism. And sine hyperbolic x plus y is that sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. And cosine hyperbolic x plus y is that cosine hyperbolic x cosine hyperbolic y plus sine hyperbolic x sine hyperbolic y. Therefore cosine hyperbolic 2x is that cosine hyperbolic square x plus sine hyperbolic square x. It is that 2 cosine hyperbolic square x minus 1, and 2 hyperbolic x plus 1. And so sine hyperbolic 2x is that 2 sine hyperbolic x cosine hyperbolic x. Therefore tangent hyperbolic 2x is that 1 plus 2 hyperbolic sine x plus 1, and also 2 sine hyperbolic x cosine hyperbolic x. When you multiply cosine hyperbolic square x in numerator and denominator, and it is 1 plus tangent hyperbolic square x, and also it is cosine hyperbolic square x plus sine hyperbolic square x, then 2 tangent hyperbolic x. Yeah, okay. Therefore, it is the 2 cotangent hyperbolic 2y is that tangent hyperbolic y and 1 plus tangent hyperbolic square y minus 1 over tangent hyperbolic y. Then it is tangent hyperbolic y. Therefore, it is consistent with the previous result. Here, let's example for the case j equal 1/2 and gj is 2 and magnetic field is 1 Tesla. Then y is that gj b mu b j and kbt. When you calculate this, it is similar to the 10 to the 2 times 10 to the minus 3 at 300 Kelvin at room temperature, which is enough small to expand as a power series. Therefore, cotangent hyperbolic y is that 1 over y plus 1/3 y minus 145 y cubed, like this. Therefore, let's estimate for small y, the Brillouin function. Here is the Brillouin function, and so j equal to then let's expand this term 2j plus 1 over 2j, and cotangent hyperbolic y can be expanded two j over 2j plus 1y plus 2j plus 1 over 6j y minus and so on, minus 1 over 2j over y plus y over 6j. Then the first term is 1 over y, and this term cancel with each other. Therefore, it is 2j plus 1 square over 12j square y minus y over 12j square. Then it is y over 12j square, then 4j square plus 4j plus 1 minus 1. Therefore, it is y over 3j j plus 1. Therefore, it is a Brillouin function. And here, magnetic susceptibility is the mu 0 m over b mu 0 over b, and magnetization is that n gj mu bj and j plus 1 over 3j, and y is that gj mu b bj over kbt. It is y. Here, and the b cancel, and the jj cancel. Therefore, here 30 kbt and n gj square mu b square mu 0 j plus jj plus 1. Here, let's define that n mu 0 mu effective mass square, and it is also 1 over t dependence. Mu effective magnetic moment is that gj mu b and square root j plus 1. It is the effective magnetic moment. Effective magnetic moment, it is need to remember. When I make a red box, you should memorize this formula because it is very important, and also here should be remembered, because from the measurement in experiment you can measure the magnetic susceptibility as a function of temperature. Then it should have the 1 over t dependence. Then you can write that 1 over chi versus temperature, there should have a linear behavior. And from the slope is that it is a c over t. From the slope, we can estimate the c, and the c is that n mu 0 mu effective mass square 3 kb. Therefore, we can estimate that the concentration of magnetic moment n, and mu 0 and kb are constant, and therefore from the estimation of c we can define that mu effective mass. Mu effective mass contains for the gj mu b can be considered. Here as gj is the lambda g factor, 3 half plus s plus 1 minus l plus 1 over 2j j plus 1. It is a lambda g factor. From the theoretical estimation, not theoretical estimation, but just only the magnetic moment information, the gj and can be expected, and therefore we can estimate that j value total magnetic moment, and from the we can compare with the theoretical expectation and the experimental finding, and therefore by measuring the magnetic susceptibility versus temperature, and we can estimate that the total angular momentum of the system. Therefore, it is important in experiment.